So, what to do if I am bored? Uh, Many options, uh, but let's instead work on a quantum machine learning project. Hello YouTube. So, welcome to this video. And in this video, we will be working on a quantum machine learning project, a quantum classical hybrid machine learning project to be very precise. And before I just start, let me be very clear with the prerequisites. So the first and very important prerequisite is Python. So you should be familiar with Python. And the second prerequisite is a basic understanding of machine learning, at least just the theory. So you should know what is a regression problem, what is a classification problem, and a basic familiarity with TensorFlow. With TensorFlow will be surplus. But if you don't, if you are not aware of TensorFlow, then you can just type in Google. You just Google it, or on YouTube, just search for image classification with TensorFlow 2.0, and I think you will get some good examples. Just go through it, and it will be really simple, and you will be able to move further with this particular project. So with that said, I also wanted to clarify that this particular project is performed on Google Colab. So no system requirements are necessary, no particular system requirement. Everything is done on Google Colab, and yeah, I think that makes everything very clear. So let me just read the title for you. So it is Binary Image Classification on Fashion MNIST with TensorFlow Quantum and Cirq. So binary image classification is nothing but a simple image classification problem that has two classes. So if you, after you have trained your machine learning model, given a new image of either of the class, the model should be able to predict the right class. That's what you mean by binary image classification problem, right? Now let us come to the second part, which is Fashion MNIST. So Fashion MNIST is a very popular benchmark data set that consists of a total of 10 classes that range from t-shirt and trousers and etc. So note that we won't be using all the 10 classes. We will be working on only two classes. So we will filter the original Fashion MNIST dataset, and we will be working only on two classes out of the total 10, right? Now let me just come to the more interesting part of the title, which is TensorFlow Quantum and Cirq. So if you are familiar with the TensorFlow, it's good, but not. Let me just tell you that TensorFlow is a framework by Google for classical machine learning. And as you might have just guessed, a TensorFlow Quantum is the quantum analog of the actual TensorFlow. And TensorFlow Quantum will help us to work with our quantum classical hybrid machine learning problem. And now let us come to the last part, which is Cirq. So again, Cirq is a framework by Google for programming quantum computers. Uh, so it is so just it can be used for various things. Cirq. So note that quantum is in various fields, all the way from quantum cryptography to quantum information theory and whatnot. But in this particular project, uh, we will just use Cirq for machine learning, quantum machine learning. But you can use Cirq for other things as well. So that's a point that I wanted to highlight. So with that said, let's go to the official overview page of Cirq. So you can see open source framework for programming quantum computers, and it's in Python, and that's why the first prerequisite was Python, because I cannot teach you the basic Python here. Uh, so this is the simple example of running a quantum circuit using Cirq, and I will be covering Cirq in this video and the basic quantum computing that we use. So if you don't know the quantum part, it's still okay. You can proceed with the project. And with that said, let's come back to TensorFlow Quantum, the overview page of TensorFlow Quantum. And as you can see, it's a library for hybrid quantum classical machine learning. And again, they have given a simple example here of how you can use a TensorFlow Quantum. Again, if this thing doesn't make much sense, it's fine. I will explain it, what's going on. Uh, yeah, so this was just, I just wanted to show you the home page of the two tools that we will be using for our project. And another important part that I wanted to discuss in this introductory section is this table of contents that you can see highlighted here, right? So these are all the steps that we will use to work on our project, and all the sections in this video we uh, will be having according to this table of contents, right? So this is the introductory section, which is this about the dataset and QML. So I just introduced you to the topic and what are the tools that we will use. And in the next section, we will be installing the required packages. Uh, and I hope to see you there. Thanks a lot. Hello, YouTube. So in the previous section, I introduced you to the topic of this project. So what we are about to do in this video, uh, and I also told you about the prerequisites and the tools that we will use to complete this project. So let us go ahead and install the required packages and Google Colab in this particular section. And before I do that, let me just tell you about the features of our dataset. So the number of images in the trained dataset will be 10,200. And when I'm talking about the dataset, I am talking about the filtered dataset and not the original Fashion MNIST dataset. So after we have filtered and completed the pre-processing of the dataset, we will be having 10,200 images in the trained dataset, 1,800 in the validation dataset, and 2,000 images in the test dataset. So now definitely you can vary these uh, ratios and the number of images in each dataset. And the goal of this project is not to find the best split and the most optimum model or something like that, but it is just to introduce you to the complete cycle of the quantum machine learning project, right? And let us go here. So you can see we will shrink the size of every image from 28 by 28 to 2 by 2, and then the type of image will be grayscale image. So the value of each pixel ranges from 0 to 255, and there's only one channel, right? And the number of labels are 2. As I told you in the previous section, it is a binary image classification problem, and you can see which are these two labels. These are sandal and ankle boot. So we will be keeping images only of sandal and ankle boots, right? So after that, let me just help you to install the correct compatible versions of tools. So you can see here we will be installing TensorFlow with the version 2.3.1, and then TensorFlow Quantum with the version 0.4.0, and the version of Cirq will be 0.9.1. So if you use any other versions of any of these tools, then there is a slight possibility that you may face some compatibility issues and stuff. And again, here we are having some errors thrown here, but don't worry. I have completed the entire project, and there is nothing, there is no issue. We will be able to complete the project, so you can ignore these errors at the moment. So once you have done that, once you have installed these packages with these particular versions using these commands, make sure you restart the runtime so that you may not face any errors. So it's always good to restart the runtime once you have completed the installation of the required packages. So once you have done that, just come here and import these packages. So you can see a tick mark here. It means that all the packages are successfully imported, and there are no errors. So we have successfully installed all the packages, right? And one extra thing is that you can use this clear output uh, method from ipython.display. So what it just does is that it just clears the output once you have installed. So beneath this pip command, you can just give clear output like this, and it will just erase off uh, the output of the particular cell after the installation is complete. So it just looks neat. That's the purpose. I have not cleared the output so that I can show you the installation results, but you can do that for your project. So yeah, in the next section, we will be going through the data set and the packages, importing them, and I will tell you what is used for what. So I hope to see you there. Hello YouTube. So in the previous section, we successfully installed the required packages, and in this section, let me walk you through the different tools that we will need. So this is just simply importing TensorFlow. Then for data processing, as I just told you that we will not be using the complete original Fashion MNIST dataset, but instead we will be filtering the actual dataset. So for the various processing steps, we will require NumPy, which stands for numerical Python, and also from sklearn we will be using train test split for splitting our data set into train set and test set, right? So now the QML tools. So you just saw TensorFlow Quantum and Cirq, which are the primary required packages for our project, and the other is SymPy, and actually it has a role to play with Cirq, and we will see how all that goes when we will come to that part. But as of now, just know that SymPy we will use with Cirq for the for creating the quantum circuits, right? And then we come to the visualization part. So for visualization tools, we will be having this SVG circuit from Cirq, and it is just for visualizing the quantum circuit that you make, right? Which is your actually model, uh, your quantum neural network. So to visualize it, we will be using this SVG circuit and matplotlib .pyplot. It's a very popular Python library that we will use for other visualization purposes, right? So let me just import it. No errors, successfully imported. Let me just again still go and print the versions. So these are the versions, the correct versions that we wanted, and this is nothing but advanced string formatting, nothing much important. Now, as I told you, that Fashion MNIST is a very popular data set, and it comes inbuilt with TensorFlow.keras. So you don't need to download anything explicitly from other website and do anything of that kind. So from TensorFlow.keras.datasets import Fashion MNIST, and we will be using dataset as the shorthand for Fashion MNIST dataset, right? So let me run the cell, and it's done. So now here dataset dot load data, so it will load the data. So you can see I have here xtrain, ytrain, and xtest, ytest. So xtrain and xtest, we will be containing the all the images and the y corresponding labels will be stored in the ytrain and the ytest. So for the ith image in the xtrain, uh, the ith number in ytrain will uh, give you the label uh, that the class which the particular image in xtrain belongs to, right? Really simple, nothing much to explain, I guess. So let me just do this, and you can see it's downloading and it's done super fast. So again, run this cell, and again the string formatting, and just see the shape of each of your set. So the xtrain has 60,000 images, and each of that image is 28 by 28. So you have 28 by 28, that's the size of each image, and such 60,000 images you have in your xtrain, and corresponding labels are here in ytrain, right? And 10,000 images are with the xtest, and again it's 28 by 28 grayscale, as I told you previously, and the corresponding labels are in ytest, right? So that's it for the video. I mean for the section. So in this section we downloaded the dataset and had a more precise look over the tools that we will be using, and that's it. I hope to see you in the next section where we will begin processing the dataset. Thanks a lot. Hey there. So in the previous section, we uh, downloaded our dataset from TensorFlow Keras, and we just saw the uh, sizes of the train and test dataset, right? So let us now come to the pre-processing of the dataset part. So from the very beginning, I have been telling you that we won't use the complete Fashion MNIST dataset. Instead, we will filter the original dataset and keep only two classes out of the total 10 classes, right? So now is the time that we will be doing it, right? So to accomplish this task of filtering, I've just defined a simple uh, filter data method, and it takes two arguments, x and y. So x denotes the images, the independent features, and y is the dependent feature or the labels, right? So what we do here, we use the uh, or condition here. So note that we had 10 classes from 0 to 9, but note we only want the label, the classes that have label 5 and 9, as you can see here, this here. So if we have any class other than these labels, we want to eliminate it, and we only want the images and the corresponding labels, which are 5 and 9, right? So to do that, I have used this simple condition here for or. So for or, we know that if either of the two condition is true, then the output is true, right? So the provided label is either 5 or 9, then the value for this variable keep will be true. But if the label is neither 5 nor 9, then this uh, value for this variable will be false, right? Once we have this variable, then using the same variable, we perform this condition on the two data, our independent features and dependent features. So we just filter this out using this condition, right? And we get our new x and y. So once this is done, the x and y now only have the labels and the images of the two classes with labels 5 and 9, the ankle boot and the sandal, right? So once we have that, another task that we would like to do is changing the labels to boolean, and this is just a simple requirement. So we will be changing it to true or false, just like 1 or 0, right? So, and for achieving that, we'll be doing this, y is equal to 5. So if the label is 5, then the corresponding value for y will be true, and if the label is 9, then the value for y will be false, right? And I think that should be clear, but if it is not, I think it might be due to this thing here. And to explain that, I've just written a little code here. So I just defined a list with 4 elements, 3, 2, 3, and 4. And then I use the for loop to traverse through it. And you can see I just made the same condition here as this one. So I want you to see what the output actually does come. And I've kept the condition I equal to 3 or I equal to 2. So it means that it should print 2 when the value for I is either 3 or 2, and it should print false if the value for I is neither 3 nor 2. And if you look at the list here, for the first three conditions, it should print true, and for the last condition, it should print false, right? And if I do that, you can see that's what the output is. So I hope I have clarified uh, your doubts, if any, for this condition, because this is a little unusual. You may usually not use this, right? And this is simple masking, so nothing much about it. And yeah, I think that's done. And I think I'm not executed this cell. Executed. So now what we do here, we just filter the train set. So we use our method filter data and pass the train set, the X train and Y train, and we do the same for the test data set. And if I do that, it's done, right? And now if I look at the shapes of, then you can see definitely it's 12,000 images in the train data set and 2,000 images in the test data set. So definitely the size of the data sets have shrunk from 60,000 and 10,000 to 12,000 and 2,000 respectively. Yeah. Now let us just have a look at the one very first example from the X train, and for that I will use matplotlib. So initially I'll just print this uh, line that helps us to see the label for the particular example, right? And then I just use plt.imshow to display the image at xtrain and color bar, so we can see the range of the values of the pixels and the title, right? So you can see it already does exist, and let me just, yeah. So you can see this image has uh, size of 28 by 28. If you concentrate, you will be able to realize that. And the other thing that is important to notice here is that the pixel value ranges from 0 to 255. It's 250 here, but it's actually 255. And we know that because it is a grayscale image, right? So you can see this is the image with label false. And if you recollect, the label will be false if y is 9 and label 9 corresponds to ankle boot, and that it is, right? So this is the visual representation of your data set if you wanted, or maybe you were not aware of the Fashion MNIST. So this is a simple visualization of the first training example that you have in your X-train, right? Now, before moving further, it's important that we normalize the images. So as of now, as you can see, you with this color bar, that the value of each pixel can range from 0 to 255, but we don't want that. We want our values of every pixel to range from 0 to 1. So why do we do that? It just helps for faster training. Again, we are not using something very complicated model in the example, but yeah, it's a good practice to do. So we will just normalize the images. Definitely don't do this on the your label data set. It is just for your images, because the value for images range from 0 to 255. So we want that range to get to between 0 and 1, right? And we have done that. We again have a look at the image, and you can see this time on the color bar that the value range is from 0 to 1, right? So we have successfully changed the range of the pixels, and you can see it still looks the same as it looked before, almost same. I think it's same. Now the next part is to change the shape of the uh, data sets of the images here. So note that uh, uh, this step is only for feeding the TensorFlow. So while you are giving input to the TensorFlow model, you don't want shape issues, that some layer output is not compatible with the other layer output, or error in the input, something like that. So to avoid anything of that, we are just reshaping our data set here. And let me just do that. You see it's done. So again, note that xtrain dot shape 0 here denotes the total number of images in xtrain. So if I'm not wrong, we had 12,000 images in xtrain, right? So it's just 12,000 here. So this is just 12,000, and for x test is 2,000, right? And this is the shape. So 28 by 28 by 1, and this 1 here actually denotes the number of channels. So this is a grayscale image, so just 1. But if you say you are working with RGB images, maybe, then you would be having 3 channels. So the number here would be 28 by 28 by 3 in that case. But that's not the case here. We are just having 1 channel, and this is the shape of your image. It is 28 by 28, right? So I hope that is very clear. Now we have come to a very important part here. So note that we cannot directly feed this 28 by 28 image as our input. And why is that so? Because look that the quantum computers that we have now are not very powerful, right? They are not something that can handle very large number of qubits. So it's important that we downscale the image and reduce their sizes, so that we can feed it to the quantum part, TensorFlow Quantum here, right? So you cannot exceed particular limit, and you don't want to just directly just imagine 28 by 28. Let me uh, tell you how many it would require. 28 by 28, 784. For a classical computer, it's all fine and good, but that's just not possible for a quantum computer. It's good to have your size at least below 10 or max below 30. But you can see here we are resizing our images. In fact, it's better to say we are downscaling the images to a shape of 2 by 2. So just 4, right? So from 28 by 28, we are downscaling it to 2 by 2. So it's easy for working with our quantum part, right? The TensorFlow quantum, and we also change it to numpy. So it's a numpy array now, and we do that, and we now again store it in the variables xtrain and xtest respectively for the training dataset and the test dataset, right? Now, if you have no. Now, if you have a look, yeah, now you can see that your 28 by 28 is now just 2 by 2, right? It's just ranging from 0 to somewhere 0.7, maybe 1. This is just respect with this particular example, but it ranges from 0 to 1. And we have 4 uh, uh, images, 4 pixel values here, right? So maybe if I just change here, you might be able to see another example. See, so this is another example from our data set. You can see 4 values, and now we have successfully downscaled the images. Now I think the preprocessing is almost done, but the only last step that we need to do is splitting of train dataset into train and validation dataset. So if you are aware of machine learning, we have these 3 datasets: training, validation, and test. So so far we just had training and test. So we also want a validation dataset, and to do that, we will use the train test split method from sklearn, and we will pass our original and training data set that we just processed in the previous step, and the test size is 0.15. So how much you want to keep for your validation data set and how much for the trained data set. So for the test size, and random state is 0. So it randomly selects some examples from the training data set and puts it into the validation and some into the training, right? So random state helps you to replicate it. So when you put in a random state, you can still replicate the same sorting of every particular example, right? So let's just do this. Done. And you can already see this shape, but let me just do it once again for you. And now you can see we have 10,200 images in the training data set and 1,800 in the validation data set. So yeah, so congratulations, you now have successfully uh, pre-processed the training data set, which is Fashion MNIST, a very popular data set, and you now have some clarity that how you can work with the classical data set and use it for your quantum machine learning project. So that's it from this section, and I hope to see you in the next section where we will start working on the data encoding. Thank you. Hey there. So in the previous section, we completed pre-processing for our data set, and now we will start working on the data encoding part. So what is this data encoding? So remember that we had pixel values as our independent features, and the values were like 0.438 and 0.5368 or something like that. And it's not possible to feed such values directly to a quantum circuit, which is our model basically. So we need to encode our data set such that it's possible for a quantum circuit to read it, right? Uh, and there are various techniques for data encoding, but maybe I will make some separate playlist or video on all the different techniques that we have for data encoding. Uh, right now, we'll be using binary data encoding technique, right? And you will see what it is in a moment. But before that, what are the steps that we will be going through in this data encoding process? So the first is binary encoding, and the second is converting Cirq circuits to TFQ tensors. So leave the latter part right now. It will require some background quantum. Let's just talk about the first part, and in fact, this is the part that we will be walking through in this particular section. So let's right away jump into it. So again, you can see here, I have just reshaped the data set. They just flattened the images. So previously we had 2 by 2, and now we have 1 by 4. And why did I do it now and not previously? Because I think just a 1 by 4 image would not look good, but uh, this 2 by 2 image looks good. It's a square image, right? So it's more easily comparable to this 28 by 28. So maybe I thought it's a good idea here to do this. And again, it worked very well everywhere. So no issues. And to feed our images to the TensorFlow ahead, it's important that we make this conversion. So it becomes a necessity here that we flatten the images, right? And flattening the images is the first step, and execute it, right? So this is the same technique of reshaping that I think I used previously for some pre-processing part. Now, let's first process X-train, and then we will move on to validation and test data set. So I just printed this X-train. Let me just change the value, maybe 1. So yeah, you can see here we have all these different values, 0, 0 0.9, 0, 5, whatever, and all these various float values. So we, as I just told you, we cannot feed these values directly. We just need a way to encode this in our quantum circuit. And what is this quantum circuit? I will be talking that in the next section. So don't worry much about it right now. But it is a circuit, and we need to encode these values into that circuit, right? So how do we do that? And that's where these encoding techniques come into the picture. So I have used here binary encoding. Uh, and why did I use this? Because it's really simple to understand. You don't need any background in quantum computing to understand this thing. Uh, so there are other techniques as well for encoding, like amplitude encoding, for example. But it would require some basic understanding of some mathematics with respect to quantum computing. So to avoid that part, I've just used simple binary encoding here. But don't worry, on this channel you will also learn about all those encoding techniques, so you don't need to worry about that. Let's focus on the uh, binary encoding. So as you can see, I have just defined a method for binary encoding, and which takes two arguments here again, x, which is our which are our images, all the images, and this threshold 0.5, and I just set this threshold to 0.5 because our values range from 0 to 1, so I thought 0.5 would be a good choice. So let me tell you what is this binary encoding after all. So binary encoding is very simple. So see, we have here these values uh, 0, 0, just 0 0.9, 0 0.7, and 0 0.8, for example, right? So if my value is greater than 0 0.5, I will just make it 1. And if it is less than 0.5, less than or equal to maybe, then it's 0, right? So all these values are just encoded as 0 or 1. And this is binary encoding. It's that simple. Let me just repeat again if you have not understood. So this is, yeah, I've just decided a simple threshold. You can vary this threshold definitely. So what happens is that, see, let me just go back to the previous one. Right now, again, yeah, we have two values below 0, 0.5, and two values above 0.5. So you can see the first two are below 0.5. So therefore, when I apply binary encoding, both of these values will be changed to 0, and both of the latter two values, which is the value number 3 and 4, will be changed to 1 because they are greater than 0.5, right? So this is the simple technique of binary encoding, and I will let you know why do we do this, uh, because it's important to understand that, because the quantum circuit cannot just directly take in values like that. You have to encode it in some way that is a component of circuit, right? So you need to encode the values in such a way. And for this, uh, as you can see here, we just use simple logic again. So just you can see here, I just encoded images list here. Just defined a simple list. Then I'm traversing through the for loop. So this X is nothing but our images, and I just defined a simple list comprehension here. So the value is 1 if j is greater than threshold, or else it is 0, right? And what is this j? This j is nothing but the variable that is traversing to this image, right? You can see it here. So image is nothing but the image in our data set of images, and this image of 0 just gives you the all the 4 values, right? So you can traverse through each of the value in your image, right? And therefore encoded image, you get all these values in the encoded image, and then you append that encoded image to your list of encoded images, right? And then you return a numpy array of encoded images, right? So that's a simple binary encoding. And let me execute this, and successfully executed. And if I encode a train dataset, it's done. And you can see it's 0011. So just as I just told you, that anything greater than 0.5 will be 1, and anything less than or equal to that will be 0, right? So that's it. We have successfully applied binary encoding. And maybe that one thing that you might feel is that we are losing information, right? Because these values 0.4156 and something, and we are just downscaling it to 0, then we are losing a lot of information, and that's correct. But as of now, we uh, don't have much choice, because we want to encode our data into a quantum circuit, so this has to be done. Again, there are various other techniques that can minimize this loss of information, but as I told you, it will require some background in quantum computing, and I don't want that to happen here. Because I won't be able to teach it here, it will require some other playlist uh, to teach all of that math. So here I just wanted to keep it simple. So we are just using binary encoding, and so the motive was to you to know that you need to do this encoding step before you can work with your data, right? So, and that we have done here. So again, let me just print the shape. So you can see 10,200 comma 4. So 10,200 rows and 4 columns. So these rows are the number of images, right? And these 4 are all those 4 values. You can see here these 4 values. So here, remember, we had these 4 values, and that were encoded to these 4 values, and that's it. So yeah, uh, for all the images, we have successfully completed the binary encoding technique. And before we move ahead, you would need some background in Cirq and quantum computing, a little practical background. So I will be telling you about that in the next section. And before we move uh, there, I hope you learned some good things here. And if don't worry about the encoding techniques and the mathematics for quantum computing, all of that will be uploaded on the channel soon. So you should be able to know all of the encoding techniques as well, right? And now every method will be practically implemented here, so you would actually know that how everything is actually implemented, right? So I think that's it for this section, and I really hope to see you in the next section where we will be talking about the basics of Cirq and quantum computing. Thanks a lot. Hello YouTube. So we were in the data encoding step for our quantum machine learning project. And before we move ahead, I want to clarify that this section of the basics of quantum computing with Cirq is also available as a separate video on the channel. So if you are a viewer who is viewing this as a separate video, then let me tell you that this is actually a part of quantum machine learning project video where we are working on a quantum machine learning project. And yeah, with that said, let me tell you the plan. So this particular tutorial is basically divided into two sections. In this particular section, I will just give you a brief idea about what a quantum circuit is and what it actually is, the basic picture of this thing. And in the next section, I will guide you through programming a quantum circuit using Cirq, which is a framework by Google, right? So without wasting any time, let's just dive in. So yeah, so this thing that you can see here, this is our quantum circuit, right? This is our quantum circuit, and this is what a quantum circuit looks like. In fact, this is the model for our quantum machine learning project. So this is the quantum machine learning model that we will be building. Uh, so before anything else, this thing, these numbers that you see here, these numbers actually represent qubits, and these numbers are actually the coordinates of the respective qubits, right? So when you define a qubit, you define it using with respect to some device, right? So if you want to execute your quantum program on a device, then there are also hardware restrictions, like because some of the gates, like you can just see in the picture, uh, a- uh, work on multiple qubits. So the position of those qubits in the hardware actually play an important role. So there are various hardware restrictions as well. So yeah, now with that said, let me clear this. And now what you see here, all these blocks are actually gates, right? And they they change the state of a qubit. So what is this state? So initially the qubits are generally in this state, right? Which is uh, 0 cat that you can see here. Okay, let me do it again. This 0 cat. This is the direct notation. It was introduced by Direct, and this thing actually just represents this vector that I am about to write. So this is in fact just this vector, but the way of writing is different. And actually, it's quite helpful, this way of writing. And you might understand this if you just look at the calculations that are involved in any quantum computing task, because all of these gates are actually can be represented by matrices. Let me just talk about that in a moment. Let's just talk about this. So this is 0 cat, right? and correspondingly there's also a 1ket. So let me give you one example to understand this. So the classical bit, as we know, can take two states, either 0 or 1. So very similar to that, a qubit can also take either 0ket or 1ket. And as the advantage goes, it can be in the 0ket and 1ket all at the same time, which is quantum superposition. So as I just introduced you to 0ket, but let me also introduce you to 1ket that you can see here. And this thing is nothing but this vector. So this is just this vector, right? These are just vectors, but the notation used is different. So that's the only case. So these are the two computational basis states for qubit, right? And this gate that I have marked here, this X block with a written X on it, is actually represents a quantum NOR gate or poly X gate. And this what this actually does is that it actually transforms the 0ket of qubit to 1ket. So it's like this, and the converse is also true, right? So 1ket can also be transformed to 0, and 0ket can be transformed to 1. So so this is one example of how a gate works, right? So this block that you see it actually transforms 0ket to 1ket and 1ket to 0ket, and this is the function of this particular gate. Similarly, we have different gates. All of these blocks that you see here, all of these double X and double Z, this H gate, this H is nothing but Hadamard gate, and it is responsible for superposition, the quantum superposition that I just talked about a while ago. So all of these gates are they have their own effects on the qubit, and quantum computing is circuit based quantum computing is all about these different effects that you give to a qubit based on the use of these different gates. So this diagram, this circuit that you see is the evolution of a qubit through time as you apply all these gates, right? And again, mathematically, all these gates can be represented by simple matrices. But I'm not going into the depth of all of that, but I will be showing you the metrics for our model, the double X gates. So you for the notion of the the quantum machine learning model, but I will tell you about it once we reach that point. For now, I think it's sufficient for you to know that this quantum circuit, is just the evolution of a qubit as you apply different gates, and different gates have their own effect on the qubit, on the state of the qubit, and all of these gates can be actually represented by a matrix. Each of these gates have their own matrix representation, uh, and I think that's a good introduction to what is actually a quantum circuit. And if I think I will make a separate video or playlist on each of these gates, maybe. In fact, I had a quantum computing project on this particular channel that helps you to understand what these gates are and how they evolve, and the state of a qubit using the block sphere representation. So I think you should check it out. It will really help you to understand uh, the single qubit gates and their calculation, their matrices, and their effect. and it is implemented using IBM Qiskit, the project, the quantum computing project, which was a quantum visualizer. So with that said, I think it's a good point to stop. And in the next part, I will be uh, uh, using Cirq to help you to understand how do you actually develop this type of quantum circuit using Cirq, right? Thanks a lot. Hello YouTube. So in the previous part, I just gave you the introduction to quantum circuit. So what it is basically, and now in this part, let us just start working on uh, programming a quantum circuit ourselves by using Cirq, which is the framework provided by Google, right? So yeah, so we will be working in Google Colab. So so that all the user, irrespective of their system, can work on this thing. And before we start working, we need to install this. So the simple command is pip install cirq or cirq as we call it. And I have already completed the installations. So I just wanted to save your time so you uh, don't have to wait while all this installation is in progress. So yeah, we are all set. And now we can start working with our circuit. So so of course the very first thing is that we need to import circ, and let's see if that happens. Yeah, you can see it's the cell is executed successfully. So we have successfully installed circ and we have imported it. So the very first thing that you think of is defining a qubit, right? Because a quantum circuit is nothing but a collection of qubits, and how you evolve uh, those all of those qubits using different gates, right? So how do you define a qubit? So let me this qubit is equal to so dot. Now let me tell you before moving ahead that there are different ways of defining a qubit. So for example, we have named qubit, as you can see, named qubit, and you can give a name to it. So when the circuit is printed, all the different circuits, the different qubits have their particular name with them. And there are also other ways of defining a qubit that are more with respect to the hardware side. So for example, if I just do line qubit, right? Cirq dot line qubit, and these are the qubits that are actually arranged in uh, one by one and on a one-dimensional structure, right? So line is one dimensional, right? So if I say define a line qubit, and I can define multiple qubits in the line using range. So here we have these three uh, qubits that are defined one after that actually exist one after another in the particular line. So uh, so they have their positions in that sequence, right, one after another on a line. But there is also another way to define qubit, and that is using grid qubit. Yeah, and note that most of the Google's chips actually uh, have follow this type of definition, right? Because these are chips, 2D structure, and for defining uh, qubits that lie on this 2D plane, we use this grid qubit method. And yeah, so again, note that when you are applying various gates on various qubits, it's important that you choose your qubits carefully, because uh, uh, different gates if have act on a different number of qubits. So if a gate is acting on say 2 qubits, and those 2 qubits are not near to each other, then that has its own disadvantages, right? So therefore, this hardware restrictions also come into the picture, and you need to think about all of it before you start developing your quantum circuit. So for this simple tutorial, I will just use the named qubit, yeah, and what should I name it? Let's just name it tutorial. Not a very cool name for a qubit, but I think that's okay. So yeah, just define this. So we have our qubit all set, and we need to convert this qubit into the circuit object, right? Because we will just working with the single qubit, but to it's important to declare it as a circuit. So we have our circuit, and to define it as we have, yeah, circuit, the circuit object, and into this we can directly apply our gates, right? So say for example, I want to apply the poly X gate that we saw in the previous part, right? Then you can do here is just give your qubit. So we just have one qubit, we give that qubit, and the circuit is ready. It's just that simple. So successfully executed, and if I just see this, yeah, see I have printed the circuit, and you can see the name is here tutorial, and this X just represents our operation of poly X gate, and yeah, it's that simple. And there are also other things like simulating the circuit and stuff like that, but for now I just want to wrap this tutorial at this point, because detailed tutorial I can just make that in before and for some other video where I can tell you about all these things in much more detail. Here the focus is more of on the quantum machine learning project. So that's it. And for the viewers who are viewing this as a separate video, I hope I was able to give you some brief introduction to what is this circuit-based quantum computing, and how do you actually create a simple circuit using Cirq. So I think that's it, and thanks a lot for being here with me, and I wish you all the best for your journey ahead in quantum computing. Thanks a lot. Hello YouTube. So in the previous 2 sections, I was talking about the basics of quantum circuit and the basics of Cirq. And now let's dive back into our project. So recall that so far we uh, we were in the uh, data encoding step, right? We have worked for all these steps that you can see in the table of contents, and we were in this data encoding step. And if you see here, uh, this is what at this moment our images look like. 0011. It's just it's just a simple Python list, right? But this is not it yet. So we need to convert all of these lists that actually represents our images into quantum circuits. Okay, and to do that, again I have defined this method here. So this is create circuit from image, and I think a very suitable name for the method. And yeah, so again the first thing that I want you to notice is this, how I have defined the qubits. So note that I have defined 4 qubits here, and it is using grid qubit, so it is a 2D plane, and it is rectangular, right? So 4 qubits that are actually placed like the vertices of the uh, of a rectangle, right? So if I just bring you back to our model example, just try to note these names of the qubits. These are just the coordinates, right, of those vertex of the rectangle, right? 0, comma 0, 0, comma 1, 1, comma 0, and 1, comma 1. So if I just draw, let me just change the color. So this is, say this is the structure, and all these qubits are placed here, right? And the fourth one, I apologize for this great masterpiece. I'm not a great artist. All right. So this is how the qubits are actually placed, and these coordinates here are just define their position, right? So I hope you got the idea. And now let's go back, and yeah. So I defined the qubits, and now I have defined the circuit object here. Right? If you see previously, I had just directly put in the gate, the polyx gate in the circuit object and just completed it there. But that's not the case here. I defined the circuit object here, and then pixel by pixel, I am uh, uh, just encoding the image as a quantum circuit. So again, this is a simple logic of yeah, so the value of this particular pixel here can be either 0 or 1, right? So if 1 implies the true condition, so if the value is 1 here, then the polyx gate is applied on the qubit, and if not, it is not applied. So remember that initially the qubits are in the 0 ket state, and if you want to change that, you do that using the polyx gate, and that's what we are doing here. So we are just converting this simple 0011 values to 0 ket, 0 ket, 1 ket, and 1 ket. So this is the simple way of how we are trying to encode this simple Python list as a quantum circuit, right? So let me run this, and it's done. Now again, I've used a simple Python list comprehension here, and I work this on, and yeah, done. And let me print the first example, the first image, and you can see 1 comma 0 and 1 comma 1. So these are the last two, right? If you just go back and see here, uh, you can see it's these last two qubits, and that should be the case, because if you look at our first example, it's 0011. So for the first two qubits, you don't need to do anything because they are already 0. But uh, for these two, you need to apply the polyx gate, so the value of the qubits changes from 0 ket to 1 ket. So I hope that makes sense. And yeah, we are done with it. The first two qubits are not printed here because no operation is being performed on them. So that's it. And now we come on to the second part of our data encoding step, which is nothing but converting our circuits to TFU tensors. And as you can see, it's just writing this simple line of code, and it will do. So as the name suggests, TensorFlow, so it's all about tensors. And again, the tensor TFQ tensors, just think of it as abstraction level. And let me just print one example again for you. So you can see this. It's difficult to read, but just think of it as some abstraction level. Uh, so it is just way how TensorFlow Quantum works. So just the main part is just encoding your classical data of those Python list into this quantum circuit. That's the most important takeaway from this section. So we are done with it, and if I just come here, you can see processing, validation, and the test data set. So what we had done so far for our uh, training data set, we have just applied those steps for the validation and test data set. And now the pre-processing part is all complete. And now we move on to the more cool stuff of working with a quantum neural network. So I hope you are really excited now. Uh, and I hope to see you in the next section. Hello YouTube. So now I welcome you to the most interesting part of the entire video, which is the quantum neural network. So again, for this step, we will be working in two sections. In this section, we will build this QNN, and in the next section, we will train the QNN. So let us dive into this. So as you can see, we will define explicitly one class for this, the class QNN, and this is the object related to object-oriented programming and stuff, and therefore Python was the prerequisite for this video. Yeah, so initially you can just see we have just initialized the parameters that we will require, the data qubits and the readout qubit, and then let's get into the important part. Now you can see here we defined a few methods here, and I will tell you what those methods are. And I think you can just look at here, and you can just, the name suggests what the method is for. So for this add single qubit gate, it simply adds a single qubit gate to the given index, right? So if you tell it to uh, apply a poly X gate on qubit number 0, then it will just do that for you. Or you can give a list of a number of qubits and it will apply X poly X gate or any chosen gate to all of those qubits. So it works on that. And very similar to it, we have another method, the add 2 qubit gates. So as you might have guessed, it actually uh, it's the same as the single qubit gate, but it is for 2 qubit gates. So gates like, for example, say C0 gate. So that works on 2 qubits. So again, you can see here very simple code for the same task, and this is just to raise this the provided list is more than 2. So if you are providing a list of qubits which is more than 2 or less than 2, then error is raised because a 2 qubit gate can be applied only on 2 qubits, right? That is simple. And in the next line here, we just simply apply the 2-qubit gates, right? Very simple to understand. Now in this here add layer, what add layer method, it's important for our model, and what it actually does is that provided a gate, it just applies that gate to each and every qubit, right? So if you provide one gate, then uh, it just gives it to all of the qubits, and you will see in a moment what I mean. So yeah, these are the methods that we give to our QNN class, and let's move ahead and come to the create QNN method, which actually utilizes the class above. So what we do here initially, we define the data qubits. So these qubits are responsible for actually uh, representing our image that we had pre-processed. So these are the images for that, and the here we define one extra qubit, which is the for readout purposes, measurement purposes. And having said that, I realize that I haven't talked anything about measurement. So let me just tell you that while working with the quantum machine learning, the three basic steps that you should know about are the, the first step, encoding your data. So whatever your data is, pre-process it and then encode it in the form of circuits. So using some gate, some way that now you can store the information of your data as a quantum circuit. And once you have successfully encoded your data as a quantum into the quantum circuit, then the next step comes is uh, applying all the different uh, gates to your circuit. So this is the main part that happens, and these are usually parameterized gates. So there is a parameter here that can be changed. So if I talk about the classical deep learning, say, then we have all those weights, and we are training the classical deep learning neural network so that we find the values which are optimum for all of those weights. And something similar is happening here. We have these gates that we apply which are parameterized, and these parameter is say theta, and theta is nothing but think of it as a way that you need to optimize, and you get it to the best value so that it gives you the correct classification results. And how do you get the output? So here comes the uh, next part, which is measurement. So measurement is a way of how you get the output from your quantum circuit. So these are the three basic parts, uh, the basic steps of working on a quantum machine learning project. And yeah, so let's get back here. And so you can see here we are preparing a readout qubit. We are applying a poly-X and Hadamard gate, and I've just done it, no specific very intention, uh, because I was not trying to build a very powerful quantum model, but it was just to show you the project. So maybe it's not necessary to apply these gates, the poly-X gate and Hadamard gate, but you can definitely experiment with these, and I really encourage you to experiment with this model. So once we have prepared our readout qubit with these two, after applying these two gates, then we call our QNN class that we just defined above, and we pass our data qubits as data qubits and the readout qubit as the readout, right? And now we have it here as the small case QNN. Now and now the magic starts happening. So we apply these cirq.xx gate. So what is this xx gate and the zz gate? So a moment ago I just told you that there are parameterized gates, and this is these are the examples of it. So uh, previously I have been telling you that all the gates can be actually represented as matrices, right? So yeah, so as you can see here, this is the matrix representation of the xx gate, right? These are the parameters, and that can, and similarly we have it for the zz gate. And when you apply a gate, actually what happens, what you can actually calculate is the matrix multiplication on the state. And I will show you mathematically how all that happens uh, in some other video, but just look at it that this is the parameterized gate and this is our parameter. As you can see here, it takes this input, and that's the uh, important part of training the quantum neural network, right? For getting the best parameter. And let's get back here, and so we have applied these two layers of xx and zz gate. Again, you can experiment with adding these layers, uh, and then at the end, before we just get the readout, we just apply another Hadamard gate. So remember that two of the most important features of quantum computing is Hadamard, quantum superposition, which is applied using the Hadamard gate. And the other important feature of quantum computing is the quantum entanglement, which is applied using a Hadamard gate and the C0 gate. So it's important. It's good to include these two features into your model somehow, because this actually gives you the quantum advantage. And there are various patterns of how you can include these things into your model, but I won't discuss it here. So once we are done with applying the Hadamard gate, we just return the circuit and the readout. So this is again, note that this is the measurement operation here. You can see the dot z here, which signifies the computational basis. So again, measurement can be done in various bases, but we are doing it here in the computational basis because it is a sort of standard. You do it in the computational basis, but it can also be done in the x basis or the y basis. The z basis is nothing but the computational basis, right? So I hope that's clear. And now we just call this method and we have our model and the readout ready. And so now let's have a look at the model, and here we go. So the font family Arial is not found. Okay, we don't care about it. So here we go, and these are the various gates that we applied successfully. Now let me just jump back to the code and tell you what we did with what line of code. So this one, this -1 actually represents our readout qubit, and these two gates were applied, the X gate that you see here and the H gate here that you can see were applied here, and the readout qubit preparation. So in these steps we apply it, and all these layers that you see for the XX gate and the ZZ gate were simply applied using the add layer method that we defined in the QNN class, and we called the method, and the all of the qubits were applied to this XX gate, as you can see here. And I have already showed you the matrix that represents the XX gate, and very similar for the ZZ gate here. And then at last we just apply the Hadamard gate, and that's done in this step, right? So the quantum model is ready, and now let's go ahead and now if you are someone who has used TensorFlow for machine learning, this part will look a little familiar to you. So as you can see here, we have tf.keras.sequential. So if you have worked with machine learning, you definitely know what this is. So sequential just means step by step in a sequence. So first you take the input, right, which is of this tf.string type. We saw the tfu layers. I just showed you one of the example for that, and you see here is the same data type for our input. And then you use this tfu.layers.pqc, and what this pqc actually stands for is parameterized quantum circuit. So I just told you that we want to optimize the values for the parameters, so we have the best quantum model, and that's what happens in the training. So while you're training your quantum model, you are trying to get the best parameters. Okay, and let's just execute this, and yeah, successfully executed. Now we come on to the other important part, which is the loss function. So in here we are using the hinge loss function, which is a very popular loss function, and I'll show you the function which actually is. So this is the hinge loss function, right? So what it is max of, so max of 0 comma 1 minus t into y. So this t take the value or plus 1 or minus 1. So t here just represents the target label, which is either plus 1 or minus 1, and y is your output from the model. So uh, correspondingly, this loss function, it will be calculated using this function. So the loss function helps your quantum model to know how bad it has performed on particular example, and help to optimize using the optimizer. And which optimizer are we using? We are using the Adam optimizer. And before getting to that, let's just go to this. To use the hinge loss, we need the labels as 1 and minus 1, and that's what we are doing here. Using this simple list comprehension, we are just converting the labels to 1 and minus 1, so that we can work with our hinge loss. So just first, okay, not executed this one, sorry, and let me change the value here. So minus 1, so we have 1 and minus 1. So if I get back to the loss function here, so say your target uh, target label is say minus 1, and you actually get minus 1, then minus 1 into minus 1 is 1, and 1 minus 1 is 0. So 0 is 0, so no loss, right? Because your prediction was perfect. But if it's minus 1 and plus 1, then it's 1 plus 1, which is 2, then the loss is 2. So it just tells you that the prediction was not right and there is a loss. So there is something bad happening. So that's the simple hinge loss. And from hinge loss, we come to the hinge accuracy, as you can see here. So I think you might have come across this hinge accuracy while working with support vector machines, I guess. So this is a simple metric that we use to uh, assess our model. So while the training is going on, how do you understand that it's working well or not? So the hinge accuracy is used to for as for the as the metric, right? So for the last time, before ending this section, let me revise what all things we did here. We saw the QNN class, then we saw the QNN method that uses this QNN class to develop the quantum model. Then we used TensorFlow Quantum parameterized quantum circuit layer for getting for loading our model. And then we also saw that what is the hinge loss function, and correspondingly we have hinge accuracy. And with everything set, we are now ready to train our quantum machine learning model, to be more precise. So that's it for from this section. I think this was the longest section, and I hope to see you in the next section where we will train the model and visualize the results. See ya. Hello YouTube. So welcome to this another exciting section in this video. So in the previous section we completed defining our uh, quantum machine learning model, the loss function, the metric, which is hinge accuracy. And with all of that done, let us just dive into the training part, which is pretty simple. So I think I have not executed this cell. So with that done, let's come here. So we need to compile the model first, as you know, before we start the training. So here we need to tell what is the loss function, which is we directly use tf.keras.losses.hinge, which represents the hinge loss function that I showed you in the previous part. Then, as I told you previously as well, the optimizer that we use is the ADAM optimizer, which is a very popular optimizer in deep learning. And the metrics is the hinge accuracy, right? So all of these three in place, we are all set to compile the model, and the compilation is done. Now it's time for training. So just like the classical model, it's model.fit. So we provide the training data, we define the batch size, epochs, and the validation data. So go for that. And the training has started, as you can see. You can see the accuracy validation is more. Okay. And yeah, I just forgot to tell you about the learning rate. So learning rate, we have set at 2.001. You can experiment with these. We have defined 10 epochs, and it's already on the 8th, and the loss has decreased considerably, and it's yet decreasing. Maybe I should have increased the epochs. Never mind. So now the time is to evaluate our quantum machine learning model on the test data set. So right, for we have just trained and validated the model, but now it's important to see how it performs on the data it has never seen before. So if we do that, so you can see a good accuracy of 0.82. So it's 82% hinge accuracy, and the loss is around 0.37. So I think that's pretty good for a very naive, simple quantum machine learning model. And Now let's visualize the results. So these are the new results. It's a model accuracy, and you can see initially it was low and then it just went up. And now again also visualize the loss, the standard loss curve. Initially it was high, and both the train as well as test loss starts decreasing later on. So yeah, so this chart shows how accuracy changes over the epochs, and this chart shows how the loss decreases over the number of epochs. So this is how this just represents, yeah, the training of your quantum machine learning model, and these are the two standard visualizations that is not normally used in a machine learning project. So yeah, that's it. And as the last step, I will save the model weights, and the model weights are saved. So all of your work is saved now because you have saved your model, and that just concludes the project. So as references, uh, I will also put these references in the uh, description, and uh, these are just TensorFlow Quantum tutorials. So the TensorFlow Quantum themselves have put up their simple tutorials for getting started. The Cirq tutorials, they have also put it there, and the other two are the two research papers that I think will help you to deepen your knowledge on quantum computing. So I really hope you read these two research papers, and maybe I will try to explain them as well on the channel. But I really hope you download them and you actually have a look at it. So with that, I conclude this project, and I really hope that you try to experiment with the model, uh, with the losses, the accuracy. Try to just change different things and see what happens. And I hope to see you in the next section where I will be discussing a few future plans. Thank you. Hello, YouTube. So I welcome you to this last section of this video, and I really want to congratulate you if you have made it this far. Not everyone can finish what they started. So with that said, I want to discuss a few future plans, and I would also like to share some possibility of modifications in the project that you can try to work with. So the future plans for the channel is I will be uh, trying to get into more of hands-on theory uh, with respect to the quantum computing and various gates. I already have a project, quantum computing project, which is a quantum visualizer that helps you to visualize the single qubit gates on block sphere, how they affect the state of a qubit. And another project is coming that will help you to understand how you can actually use quantum superposition in a very fun way. And after that, another project will be uploaded that will be about quantum entanglement. And the reason for doing is that is uh, quantum superposition and quantum entanglement. Both of these concepts are at the heart of quantum computing, and so it can help everyone who is into quantum computing, not only the quantum machine learning people, but also quantum cryptography or quantum information theory. Anyone who might be interested in the quantum field will be benefited from these projects. So coming back to the quantum machine learning part, uh, I hope you try to experiment with the model, try to apply different gates, if you're already familiar with quantum computing, definitely. If you're not, maybe you should try to stick with this channel because it's more of about quantum computing, and I will try to help you as much as possible, try to teach you as much as possible, and so that you can get started with quantum computing and quantum machine learning, hopefully. And for with respect to this particular project, uh, you can try to change the loss function. You can try to experiment with the metric. So we used hinge accuracy, but you might just try to change that. And for doing that, you might need to change the loss function. Try to go more deep into TensorFlow Quantum. It's a great way of working on trying to get into quantum machine learning. And that's it. I think enough of talking, and I will see you now next in hopefully in one of the projects. Right? Goodbye.